The current artificial intelligence industry is defined by brute force. Tech companies are buying and deploying silicon at a scale rarely seen in human history. OpenAI has committed upwards of $400 billion on data centers. Microsoft, Google, and Amazon are allocating hundreds of billions more. The entire economic structure of the industry assumes a simple rule: the company that builds the largest possible facilities will secure the most capable AI. In practice, this means accumulating miles of server racks, securing localized power grids, and installing massive liquid cooling systems. But this method of brute force scaling is hitting strict physical limits. The energy grids cannot support infinite expansion, and the hardware supply chains cannot manufacture advanced accelerators fast enough. Because of these constraints, the economics of scale are degrading. Each additional dollar spent on raw compute is yielding slightly less capability improvement than the dollar before it. While the capital-intensive scaling race dominates public attention, researchers are quietly running a parallel strategy. They are rewriting the algorithms to require a fraction of the resources. This alternative approach replaces raw compute expansion with strict mathematical rigor. Instead of building wider networks, researchers are cutting highly optimized, compressed pathways through existing architectures, fundamentally changing the game. Two recent announcements highlight this shift directly: Google's Gemma 4 architecture and a specialized academic algorithm called TurboQuant. Together, they prove that developers can radically shrink the footprint of a large language model while maintaining its highest reasoning capabilities. Because these frameworks are entirely open source, they bypass the massive paywalls and centralized control maintained by the largest tech monopolies. The next phase of AI development relies on engineering the most elegantly compressed architecture, rather than simply hoarding the most silicon. For years, the scaling laws dictated a simple equation: adding more parameters, the numerical weights inside a model, naturally produced better capabilities, but drove inference costs through the roof. Google's research teams abandoned this volume-first approach when they designed the Gemma 4 open-source models. They targeted an entirely new metric called intelligence per parameter. They deprioritized structural size and focused entirely on algorithmic density. During training, the methodology forces every single numerical weight to extract and hold the maximum possible semantic utility. No parameters are wasted. In benchmark testing, these mathematically dense structures consistently outperform older, bloated models that are several times larger. Open-source developers are using this cost efficiency to rapidly close the capability gap that once separated them from commercial labs. By delivering near-frontier intelligence at a fraction of the computational footprint, these optimized open models remove the core pricing leverage held by closed-source providers. To understand why this compression matters, we have to look at the physical hardware accelerators required to run massive models in real time. Deploying large context windows hits a strict mechanical bottleneck known as the key value cache. When an AI generates a new word, the KV cache must store mathematical representations of every previous token. The memory requirements scale linearly. As the prompt gets longer, the cache rapidly bloats outward until it overflows the capacity of a standard GPU. Running a 1 million token context window requires tens of gigabytes of physical memory strictly to hold that cache overhead. This extreme memory bloat physically locked advanced capabilities out of consumer devices, trapping the most useful models inside centralized data centers. A new algorithmic technique called TurboQuant attacks this linear memory bottleneck directly. The process begins with step 1, PolarQuant vector rotation. The algorithm mathematically transforms the cache representations, rotating the data blocks along a three-dimensional axis to prepare them for compression. The total volume remains identical, but the geometric realignment preserves all the semantic information content within a highly structured grid. Pre-sorting the data geometrically is the strict prerequisite. It ensures the system can perform extreme volume reduction later without lobotomizing the model's actual reasoning skills. Once the grid is aligned, the system initiates step 2, Quantized Johnson-Lindenstrauss compression. This leverages a mathematical theorem of high-dimensional geometry to slice a plane through the vectors, collapsing them into a drastically smaller physical footprint. This single-dimensional slice reduces the entire KV cache by a factor of 3 to 5. The entire data load fits cleanly back inside a standard graphics card. The geometry guarantees absolute accuracy. The algorithm perfectly maintains the relative distances between all internal data points, meaning zero knowledge is lost. Massive context tasks, analyzing 100-page documents or running complex autonomous agents, can now execute cleanly on consumer microchips. TurboQuant and Gemma 4 belong to a much larger stack of interlocking efficiency algorithms. They run in parallel with architectural upgrades like mixture of experts routing, sparse attention mechanisms, and speculative decoding. This chart shows the direct result of stacking these techniques. The raw computational cost required to process a prompt is plummeting. The cumulative effect drives the execution cost of a frontier model down by a factor of 10 every single year. For hyperscalers, this compounds profit margins on every API call. For startups, it virtually eliminates the infrastructure barrier to entry. Cost reduction is currently outstripping raw capability scaling. The economic center of AI is actively migrating away from pure hardware infrastructure. These software breakthroughs scale directly into global geopolitics. Algorithmic efficiency operates as a strategic weapon. The ability to compress intelligence allows nation-states to bypass physical hardware embargoes. When countries face strict export controls on advanced NVIDIA silicon, they compensate by heavily optimizing open-source architectures to run on older, unregulated hardware. Mathematical density provides a direct route to sovereign AI independence for smaller economies that cannot commit hundreds of billions of dollars to data center construction. On the environmental front, extreme algorithmic compression serves as the only mathematically viable check against projections that AI will consume 8% of all U.S. electricity by 2030. Efficiency has moved from an operational cost-saving measure to a primary lever of national technological resilience. The ultimate destination for this rapid compression is moving execution entirely out of the cloud. We are leaving a brief period dominated by centralized monopolies and transitioning to localized, on-device intelligence. Within a few years, capable frontier models will run directly on phones, laptops, and local network edge devices. This shift guarantees zero-latency execution, total data privacy for enterprise applications, and immunity from network outages. Capital-intensive megamodels will continue training inside secure bunkers, but the democratized, highly efficient models will interface directly with the global economy. The current obsession with pouring concrete for massive data centers is a necessary but strictly transitional phase in the hardware lifecycle. The defining narrative of the next decade will be decided by how elegantly intelligence can be compressed to run everywhere.